coaster, and this drop right here is our first point, which is right here, as you can see by the divots. And then as it drops to the loop, our second point is right here. And the height of this dowel is 90 centimeters. The height of the second dowel is 40 centimeters, and the height of the third dowel is 32 centimeters.
We face while building a roller coaster is first of all this hill. At first we were afraid that there'd be too much acceleration, this hill would be too steep. And so what we did was we fixed the problem by if this makes sense, cutting off some of the hill, so the hill would be less steep and shorter too. And so we cut it to a good distance till it worked. So when the hill worked, the first loop was pretty good actually. It managed to go through the loop, but then towards the second loop, it didn't have enough speed to go through the whole loop. So what we did was that we made the loop smaller, and so that actually worked because there would be more acceleration, so that way the model could go through. And so what we're going to show you all the calculations and what scientists use to see to find if the roller coaster is safe or not. So if you go to an amusement park and you go on a roller coaster, scientists examine using all these calculations that we're going to show to make sure that the roller coaster is safe for all
Free body diagrams. This line represents the downhill slope of the roller coaster, and this is the roller coaster part. This is the natural force, and this is the weight of the cart, which is mass times gravity. This is going to be 0.1 on our roller coaster. On our roller coaster shows the clockoid loop, which is a loop that isn't a full circle, but it's more oval. And then this is our cart, and this time the natural force is pushing down, as well as the weight. 0.1, since it's not a loop like 0.2, we're just going to calculate the regular force. But because 0.2 is a clockoid loop, we're going to calculate all the circular motion forces. The force equation is force natural plus force W, which is force weight. In this circumstance, force natural equals force weight, so it would be 2 times mg, because force weight equals mass times gravity. This would get us 2 times the mass, which is 0.00838 times gravity, which is always 9.81. Then we get 2 times 0.0822878. We then can simplify this to get force equals 0.1644156. The equation for circular motion forces is force equals mass times acceleration. So for 0.2, force equals mass times v squared over r. This is the equation for circular motion to find acceleration for circular motion. Okay, so we do force equals 0.00838 times the velocity, which is 1.804 squared over the radius, which is 10.5. This gets us force equals 0.002597 newtons. Potential energy equals 0.008 kilograms times gravitational force, which is 9.8 meters per second squared, plus the height, which in this case is 0.94 meters. So this calculates to 0.074 joules. And the kinetic energy for point A would be 0 because at the top of the hill there's no velocity. So the mechanical energy would be 0.074. Okay, so I found the potential energy at point B, which is mass times gravity times the height, which is 0.008 kilogram times 9.8 meters per second squared times the height, which for this is 0.4 meters. And so this turns out to be 0.031 joules. And then, so then I found the kinetic energy, which this has kinetic energy since it's moving. And since we know that kinetic energy equals negative of potential energy, so tell that 0.031 joules equals the kinetic energy formula, which is half mass velocity squared. And so that is half. And we don't know the velocity squared. So from this equation, we can tell that the velocity is 2.78 meters per second. And so for the mechanical energy for point B,
will be P plus KE, which is 0.062 joules. So we know the speed of the initial point, which is 2.78 meters per second. And so now we want to find the speed of the final product, speed of velocity. So in order to do that, we do PD initial plus KE initial equals PD final plus KE final. And so this will essentially be mgh initial plus half mv squared initial equals mgh final plus half mv squared final. And so from this, we can get rid of all the m's because we can't cancel out. And also, I know what v squared is. And so from all this, we calculate that 13.042 equals 3.924 plus 0.2 velocity squared. And so then you calculate that the velocity equals 6.77 meters per square. And so this is the velocity as the final point, and this is the velocity or speed of the initial point. So this is initial. Calculate the work done by friction by using this equation. So net work equals the final kinetic energy. So this turns out to be half mv squared. And so we can plug in what we know, which is W equals half the mass, which is 0.00838 kilograms, times the velocity, which is 0.2163 meters per second squared. And so from this, we can find out that the net work, equals 0.0019603 joules. And so this is a net work on point 1. So that's not good. Turned out for the work to be 0.074 joules. And so this is a work done on friction on point 2. Use the same equation to find the work done by friction on point 2, which is net work, once again, equals final kinetic energy, and this turns out to be half mv squared. And so, plug in all my equation, 0.00838 kilograms times the velocity, which in this case is 1.8. Turned out for the work to be 0.074 joules. And so this is a work done on friction on point 2.
Now let's talk about our research question. Our research question was, how would doubling the mass of the marble affect the circular motion force and the work done by friction? First, let's do our calculation for circular motion. So the formula for circular motion is net force equals mass times acceleration. In this instance, we're going to be plugging in v squared over radius for acceleration. Now we're going to plug in the new mass of the marble, which is 0.01676, and then plugging in the rest of the components that we already know. Once we've discovered our final answer for the net force with the new mass of the marble, we can plug it into a ratio so we can discover the relationship with the new mass, with the new net force, over the relationship with the net force of the original marble weight. As you can see, when we've solved down, each side is the same, and this shows that the net force doubles when the mass of the marble is doubled. Next, we have to calculate for the work done by friction. The equation for the work done by friction is the net work equals 1/2 mv squared. Now we're going to plug in all the variables that we already know, including the new mass of the marble, and solve down to see what we get. Once we get our final answer, we can plug it into the ratio like we did in the circular motion problem to see what the relationship between the two is. Once again, both sides are the same, meaning that the work done by friction perfectly doubles if the mass of the marble is doubled. In conclusion, we found out that if the mass of an object is doubled, the circular motion forces and the work done by friction will be doubled as well. For Content Standard 1.1, Newton's Law, 1.2, Circular Motion, 1.3, Energy, and 1.4, Work, we completed all the calculations that corresponded to the necessary standards. We were able to do this by creating free body diagrams, utilizing Newton's 3 laws of motion, incorporating the equation for the acceleration of circular motion, and applying the formula for work done by friction.